earlier this month, I built a package that lets you do elegant animated arithmetic with React Native. So a bit of a weekend project, and then a Medium article, and then here we are. And I want to mostly spend my time going over the why I built that, apart from that it was fun, and then a little bit about the how. So just before that, actually, so quick show of hands. Who here has used the animated API or has heard about it? Cool. Yeah, solid majority here, I think. That's cool. So I want to go very quickly over just the fundamentals of why animated is a thing, and then get to why my package is a thing, essentially. So, has anyone heard of the term the bridge, the JS to native bridge in relation to React Native? Yeah. Cool. So, one of the key things about React Native, just in general, is that we get to render in JavaScript. We write components and they render out JSX, and then whatever we render happens and shows up on screen through some native code. So the communication mechanism between the JS side and the native side is called the bridge. And there's a lot to be said about that. But basically, one of just the core mechanics of a React Native app is that we render and re-render and re-render from state to whatever the new UI state needs to be, and that travels over the bridge as instructions for things to then happen on the native side, for specifically things like native style properties to be set, and graphics code to run, and pixels to hit the screen, and this just happens over and over and over again. Now, how does that really work with animations? So, an unfortunate fact of how React Native works is that the bridge is slow. It's awesome, it enables a lot of things, but it's just slow. If we want to animate at 60 frames per second, or whatever the benchmark is these days, then re-rendering and sending new instructions over the bridge is just too slow. It just does not cut it. Hence, and as most of you are aware, the animated API was born. So with the use of the animated API, and again, this can be its own talk, just introducing this API, and unfortunately I don't have the time to do that. But the key thing to note about it is that it saves us from having to re-render. Instead, it reorganizes things such that we can send instructions ahead of time when we do render, infrequently. We send the setup of the animation, and then it all happens very quickly and very frequently on the native side, purely on the native side. So there's a native driver involved that receives that description of the animation and just runs a tight loop, churning out frames and actually setting the native properties of the native components. Things like all the visual properties, opacity, transforms, etc. Now, I only have one big yellow slide, so this is the one. This is the one to pay attention to. Sorry. The core API that this library exposes is centered around, and the animated is a library that comes with React Native. The core API that it exposes is called the animated value class, the animated.value class. Now that represents a value that changes over time that can drive an animation. And what the value is doesn't actually matter. So there is an actual number that changes from frame to frame, but the whole point of this is that our JavaScript code doesn't care on a frame-to-frame basis what that number actually is. That is abstracted away, and that is the native driver's responsibility to actually manage that value. And we can subscribe to callbacks, and we can occasionally know what the number is, but mostly things are structured such that our JavaScript code, our JavaScript logic, does not need to know what's in there. Now, this class exposes methods to do all sorts of things. One of them is to control animations. So we can start an animation to take a certain amount of time and to go from a certain value to a certain value, saying going from 0 to 1 over 2 seconds. And we can say, okay, now start that. And the native driver goes to work, churning out 60 frames per second of that. We can also connect physics-based, we can start physics-based animations. We can connect a spring model. Another nice thing is that we can link an animated value to a live input from an event, from the user. So touch event, scroll event, etc. We can use that to drive animations, which comes in handy when we want to show visual feedback on an animation. Another major thing, or major thing we can do with animated.value is we can bind it to a style property. When we do render, we can use animated values to say this is the property, this property of this component should be linked to this value. So whenever it changes quickly on the native thread, this component and this property of this component will actually change visually. So again, opacity or transforms or colors, things like that. And the third area of the API, which centers around this class, and this is where this talk is mostly concerned, is a set of methods that let us interpolate values to make new derived values, and more specifically to combine values in certain ways. So we can, and I'll show an example in a little bit, but one thing that this allows is for us to add, multiply, subtract, etc. Between different instances of animated values that we have in our code. And this comes in handy when we want to create more complicated effects. We may want to add a value that comes from a time-based source and a value that comes from an event source. And we want to do some calculation on them and use the result of that to actually drive the opacity of the button or the transform on the piece of text. And now we are zooming into calculations on animated values. So let's look at one very simple example. If we want to add two animated values, in this case the stored in variables called x and y, then this is how we can add them together. We use animated.add of x and y, and the result of this is itself an animated value instance. We can use it anywhere we could use x by its own or y by its own. So we can use these kind of composite values. A more involved real-world example, this is modified from an app that I actually built. This has to do with kind of a circular animation, circular progress indicator with pulsing animations. You should have seen it. It's a shame I don't have it in my slides. So in this example, phase is an animated value, and angle is just a plain JavaScript variable that holds a number. It's a constant, as far as we care. And this expression adds together phase and pi times 2 plus angle, divides all of that by pi times 2 and returns the remainder from that division. So that basically implements the modulo operator. Now this is all really nice. I really do like this library. But, by the way, side note, this is how this is what people used for keyboards before there were keyboards to program computers. This is literally a pair of keypad controllers that were actually used for basic programming on the Atari. Just thought I'd mention that. Keyboards are much nicer. So, about these calculations with animated values, there are a few things that could be nicer about this, basically. And it kind of comes back to a point, if I can paraphrase something Matt said, when you look at a piece of code, you want to just understand what it does, kind of intuitively. You don't want to spend time thinking about why it looks weird. So this really ties into that. So we're used as coders in JavaScript, for instance, and a lot of other languages. We are used to writing mathematical expressions using an infix notation. So first variable, then the operator, then the second variable. But here, we are forced to put the operator first, or what represents the operator first. We do add x, y, rather than what we're generally more used to, which is x plus y. Now, a more kind of nuanced point is about types. It's really not obvious in this code what the types of phase and angle are. Remember, I said phase is animated and angle isn't. That actually decides and dictates the shape of the code around that, the code that uses these variables. So we have to use animated.add for phase, but when we want to add something to angle, we use the plus operator. So there's just that bit of imperfect ergonomics, I would say, in this API. And it occurred to me one weekend earlier this month that it could be better. So what if, instead of what we just saw, we could just say value equals blah 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 x plus y. Something that looks a lot like just x plus y. What if instead of that second complicated expression, we could just directly write it with mathematical operators that we know from JavaScript? This, in my eyes, this is much easier to read, much easier to look after all the time. So yeah, so it turns out we can do this, and the package that I built, and I'm going to keep talking about, allows you to do that. Now, to dive into how this works just a bit, or to get kind of a better feel for it, just a quick refresher on tag templates in JavaScript. So again, quick show of hands, who's comfortable with the concept of ES6 tag templates? All right, cool. So template strings are just those strings where you can use new lines and you can use variables in, etc. Then that just makes a string. A tag template, like this one, as of ES6, is actually much more powerful than that. It's a sneakily powerful feature of ES6, and a lot of kind of new and interesting uses of it are still coming out. Because this expression is actually equivalent to writing this. Foo, the tag of the template, in the example that uses tag template syntax, foo is actually a function. It can be a function that does whatever with the templates, the fixed parts, the literal parts, and the variable parts of the string that it receives. And it can return basically anything. It can return something that's not a string. And specifically, as in our case, it can return an animated value instance. So this So this is a just JavaScript solution. Now going back to this, so my package, the package I built, is basically comes in the form of a template tag function that you can use, that you can import and use anywhere in your code. And through a bit of additional magic we'll get to in a second, this is exactly equivalent to writing the animated library code that we saw before. So just a bit about setting up with this. It is as easy as installing the package from npm, setting up Babel plugin macros if you haven't already, and you should. If you're using any kind of JS to JS transformation, any kind of language enhancing modules, you should probably check if they have a macro version, because this is much easier to set up. You set up, if you've ever set up a build, if you've ever edited a Babel config, webpack loaders, etc., that stuff adds up. So the thing with macros is that you set up the plugin once, and that's potentially the non-trivial setup to integrate with all of your tools. But after that, you just import macros off of npm, and you just use them, and they just work. So as someone who has written Babel plugins and used a lot of Babel plugins, this is much lighter weight, and it's actually fun. So you install, having set up Babel plugin macros just once for your project, and having installed the animated.macro package, you import the tag function from animated.macro, and you use it like we saw before. Now, the way this works is actually twofold. So it's a compiler, and we'll go into what that does. But an interesting fact is that it's actually two compilers. So to answer the question about performance, this all happens, like the main way you would use this as a Babel transform is at compile time.
Is this like Sweet.js?
It's sweeter than Sweet.js, yes. But yeah, it's kind of that idea, just integrated with the Babel ecosystem. So the idea is that import goes away completely. It doesn't even, if you care about your bundle size, although in React Native we care less about that. But the package literally isn't there at runtime, and there is no parsing that happens at runtime. It all gets compiled as part of the Babel transform, which happens anyway when you're using React Native. The tools are all there anyway. So as part of that, the import goes away, all the fancy syntax goes away, and it's just animated library calls. So you get all the benefits of the syntax with no runtime overhead, essentially. But I said two compilers, so a bit of trivia is that I do have a version of this compiler included with the package that does have a runtime cost, and that's literally just for demoing it on Expo Snack. So on Expo Snack, I can't actually configure Babel plugins. So and that was a really nice kind of exercise in abstraction, writing the same compiler for two targets: one that generates JavaScript code, which you would use in production, and one for demo purposes that does all the heavy lifting at runtime. And so really quick run through of the actual compiler that's involved, because this is legitimately an actual compiler of a very, very small and restricted language, but a compiler nonetheless. So we start with the strings and placeholders that make up the template, like we saw. These two kind of arrays, one of the constant parts and one of the variable parts. We process that into a stream or a soup of tokens, which is just a linear kind of representation of what comes first and what comes next. We'll see an example in a little bit. Then we parse this token soup into a structured representation, which is an abstract syntax tree. We apply set of syntactic rules to understand the structure of the expressions from the tokens. And once we have that, it's really easy to just traverse that tree once, go through all of the nodes in the tree, and convert them to the equivalent bit of JavaScript that actually needs to run for it. So to illustrate that, I'm going to look at a very, very simple expression, which computes x plus 1. So the tokens here are one placeholder, which holds the x variable, one operator, which is plus, and one numeric literal, which is 1. So having extracted that representation from the source, we apply a rule that can detect that this is a binary expression with the plus operator, which has a placeholder as its left-hand side and a literal as its right-hand side. So it's a tree. It's a small tree, but it's a tree. And then that immediately translates to the equivalent JavaScript, which is add x and 1. So we can see all of the nodes in the tree are represented, just embedded in a new structure, in a new format. So where can this go next? I have my ideas, and after I released the package, some interesting Twitter conversations started about crazier ideas for what can happen with this. But basically, one fairly obvious thing is that the actual language can be extended. There are more mathematical operations that can be represented, like absolute value and other things, maybe kind of a full math library, which right now we can only do the really basic arithmetic. Another interesting kind of avenue of exploration with this has to do with integrating this more tightly with React Native itself. So taking advantage of the fact that that this tool now exists, maybe we can make it output a kind of a better data structure, a better representation that's more efficient to send over the bridge, or we can do some, basically, and it's kind of a whole world of compiler type optimizations, essentially. We can check which variables aren't being used, all the stuff that comes with having a bit of syntax available to analyze. And one thing that I find really interesting is a similar approach can have other uses within React Native. So why stop at animations? Are there any other places where we might want to ship kind of a micro program over the bridge for it to have all sorts of side effects or effects on the native side? So people have mentioned text input. I imagine like very small event handlers that to implement some kind of effect that is just for which just incurring the cost of the bridge traffic would be too expensive, would be too slow. I had the idea of exploring maybe a canvas type API where you can send a small canvas like imperative drawing program over to the native side and then have that executed really quickly rather than sending instruction by instruction. So these are all ideas. To recap, this is about an ergonomic way to do animated maths. It's implemented as a Babel macro and a compiler that takes tag template literals as input. And there's probably more to come. Thank you.